Let's practice assigning oxidation numbers. In your course content, there are a lot of rules for doing this. And the most important one is that oxygen is always going to have an oxidation number of -2, with the exception of peroxides, which you should not see. And if the compound is neutral, like our first example, A, then the sum of the oxidation numbers should be 0. So if we know that oxygen is -2, and there are 2 of them, that means we have -4 total. So our sulfur must be +4 in order to cancel that out. Relatively straightforward. You can indicate this stuff in any way. I'm not going to do a whole lot of asking you specifically just oxidation numbers. We're going to use it as part of a bigger question. It'll help you get your final answer, so however you choose to indicate it is fine. In this example B, the compound is not neutral. We are going to have this polyatomic ion here, carbonate, so we need a -2 charge. That means the sum of the oxidation numbers should be -2. Our oxygen is still -2 itself, and there are 3 of them, which gives us -6. If we want there to be -2 left over, that means this carbon is also +4. Now this last example is applying this in the context that we're going to use it in the most often. We are usually going to talk about oxidation numbers for an entire reaction. So let's apply it here. This first one, aluminum solid, has an oxidation number of 0 because it is uncombined and it is not an ion. We can say the same thing over here with this diatomic molecule. Diatomic molecules are considered the same way, so those will be zeros. When we start with the sulfuric acid, the oxygen is -2 and the hydrogen is +1. That's also one of your rules. So we have 4 -2's. That gets us -8. We have 2 +1's. So +2 gives us -6. And that means that our sulfur must be +6. I'm going to write it down here just so it doesn't get blended in too much. Now let's look at our aluminum sulfate. Same thing with the oxygen. And you might say, we don't know what the charge of the aluminum is, so we can't figure this out. But we know that sulfate, SO4, has a charge of -2. So we can do sulfur based off of that. SO4 has -8 total. And if we want it to have a charge of -2, each sulfate ion, then each sulfur has to be +6. So we've got +6 and -2. When we add together, that it's -2 total, right? So -2 times the 3 gives us -6. So our aluminum has to be +3. This may seem like a lot of convoluted back and forth, but we will practice this a lot, so you'll get really good at it. Don't worry. Now the step we're going to apply to this next, we can go ahead and talk about real quickly. We're talking about oxidation reduction. So we find elements whose oxidation number has changed. The first one we can see is aluminum. It went from 0 to +3. Is it losing or gaining electrons? If it becomes positively charged, it is losing electrons. So we can remember Leo. Losing electrons is oxidized. And the other one that changes is hydrogen. It goes from +1 to 0. So it is gaining electrons. The other line says Ger. If you are doing a single displacement reaction, it's always going to be the stuff that's single on either side. It's going to be being involved in this. So we're getting ready to apply this in a minute so that we can use this method to find what's being oxidized and what's being reduced, and then to balance redox reactions, which are a little bit trickier to balance than regular reactions because you have to balance charge and electrons as well.